Um, Hello, everyone. I am Joshua Neimann, and I'm going to be going over Bluetooth a bit today. I don't really have a Who Am I slide, but I am the IRSXEA. I'm a fourth year here, and I'm a grad student. I'm going to apologize slightly because in a lot of places in this presentation, I did commit the sin of the wall of text. So there's going to be a lot of text. Most of it you can just skip. These slides will be up later if you actually want to go back and look at it. However, I'm going to do my best to actually point out what's important, and I'll make sure you know about the basic acronyms and stuff that you'll need to know. So the first thing I want to go over with this presentation is the differences between the two Bluetooth standards that exist. And there's actually a lot of differences between these two, so much that you can't even really call them like the same protocol. So we have Bluetooth BR EDR, which I'm going to refer to as the older style of Bluetooth. This was predominant in the Bluetooth 2.1 days, and you can almost think of it as TCP, and you can almost think of Bluetooth LE as UDP, except you can't remotely think of them as remotely the same because they use a completely different style of communicating. However, EDR is going to be very responsive. It's going to be connection-oriented as opposed to low energy, which is just going to be connection-less, and it's going to generally not have concurrent data being sent. You can also notice that there's a lot of different there's speed differences, there are power differences, there's range differences, and Bluetooth low energy basically is going to win everywhere but speed. Speed and consistency is what EDR specializes in. And they both use the same frequency. So if you're trying to pick between, if you're building something with Bluetooth and you're trying to pick between the two, pick EDR if you have a lot of power at your disposal. You want to pick EDR if you need a continuous data stream. And you want to pick LE for basically everything else. So LE is much better at being low power. You can see we have two examples of LE devices right there, a smartwatch and a tile. You'll notice that these also have completely different power budgets. The tile needs to be basically run off one battery and never be charged, and they're designed to be replaced every year or so. However, the fitness watch right there is actually something that's going to be charged every day, but both of these can use LE, and it's actually low power enough that both the tile and the Fitbit can work with some modification to make everyone happy. Generally, for EDR, you're going to see a lot of audio equipment use it. Basically, every modern Bluetooth standard for audio uses EDR at this point, but this is slowly changing, and one of the reasons for it is because of completely wireless earbuds. If you're sending a Bluetooth stream to two independent devices, it turns out it's much easier to just send it to those two devices as opposed to sending an audio stream to one Bluetooth earbud and having it send over to the other one. So before we get into BLE, which is going to be the bulk of this presentation, let's take a look at some EDR stuff. Like I said, there's a lot of audio support for EDR. And that giant list of protocols at the bottom, there's a lot. But really, most modern headphones are going to use one of those bottom three. The top two are for compatibility. However, HFP right there is the only one that actually supports using a microphone. HFP stands for something along the lines of headset protocol. And because of bandwidth limitations on Bluetooth, you kind of need HFP, which is going to use a really low bit rate, mind you, to actually send audio and receive it simultaneously. So if you've ever been on a laptop using Bluetooth headphones and your headphones are set to use your microphone from your Bluetooth headset, and you wonder why you get a significant drop in audio quality, that's why. Your computer is switching between something that optimizes for audio quality and something that optimizes for bandwidth and actually sending over both streams simultaneously. The other really important thing with EDR that you should know about is the pairing requirement. And everyone's seen this. You have to actually perform some action in your Bluetooth settings in order to connect an EDR device. So in some places, that's just holding the power button on a pair of Bluetooth headphones. And that will initiate a pairing process. And if your phone is in discovery mode, it can see that process and actually connect to the device. There's a lot of different ways that you can authenticate using this pairing process. The most common for EDR is going to be just works and numeric comparison. Numeric comparison, you've probably seen if you have like a car Bluetooth system, where it'll say something along the lines of, please verify that this number is the same number you see on your device. What's actually happening there is that there's kind of like an initial like kind of nonce for a random number generator, and that 8-digit code that you see on the screen is going to be that nonce. For just works, that nonce is just going to be set to all zeros. Oh yeah, EDR also has some encryption built in. EDR uses the Safer Plus cipher, which I hadn't actually heard of, but it was actually one of the candidates for AES before the current algorithm was chosen for that. And the encryption is pretty good. You're probably not going to actually crack that, but the weakness is going to be in the fact that you have an 8-character like initial value for that random number generator. Switching over to LE, pairing isn't required, which is going to cause some very, very interesting implications. But what that could mean is if you have like a Bluetooth device that's sitting in public, your phone can actually connect to that without like having any prior authentication or any notice on the user's part in some cases. I'll get back to that, but that's very important to note because it's a very important part of how LE works. Speaking of that, LE is, unlike EDR, which is connection-oriented, the GAP protocol, which is what LE uses, is pretty much connectionless. The GAP protocol stands for Generic Attribute Profile, and it's kind of a server-client relationship, but I think the easiest way to describe it is to abstract it out. And what I mean by that is you should consider both the central device, or like a smartphone, and the peripheral, like, I don't know, this Pi right here that is currently acting as a device. And you should add something in the middle. And that something in the middle is going to be what you write to and read to. So if you have a Bluetooth device and you want to get data from it, and you are the phone, you are going to request a read from a thing on that device. And that read is abstracted by the BLE layer, so it kind of works more like an API. I'm not sure how much sense that made. However, I can try to explain it a bit more in a few more slides. And the best description you'll probably end up getting is an article by Adafruit right there. And you can take a look at that if you're interested as well. The first part of the GAP protocol for actually communicating is a characteristic. And you can think of this as just a data value. It's a data value with a identifier, or a UUID, universally unique identifier. It's kind of like a variable that you can think of. It's what you are reading to or writing from. So if you have a peripheral like this that is advertising a specific characteristic, and you want to read from it as a phone, your phone is going to request a read from the Bluetooth chip, which is going to send a message over to this device and say, hey, what do you have? And from the perspective of this device on the application side, this is going to see the request for a read and return information to the Bluetooth chip that sends it back. Yep. All right. So moving on. I want to go to a Bluetooth service. So a Bluetooth service is essentially a collection of characteristics. We actually have one example right here. This is available if you go to the Bluetooth spec. This is one of the like general Bluetooth services that is used in the wild actually. And we have a blood pressure service that contains three things: blood pressure management, intermediate cuff pressure, and blood pressure feature. And I believe blood pressure feature is like a version number or something like that, or what it supports. But you can kind of see how these Bluetooth services and characteristics are starting to kind of work together. The last layer of this is a profile, which is just a collection of those. Predefined collection of services. However, one important thing to note here is that often Bluetooth profiles will come with implementation details and implementation like specifications. So if you're going to implement this, you should implement it this way. And BLE profiles are actually defined on the Bluetooth organization's website. You can go there, you can take a look at these profiles, and you can actually see specific implementation details, which is pretty cool. A lot of notable examples for like the generic BLE certified profiles are on the screen. A few interesting ones: heart rate. So if you have a fitness tracker or something, that's going to be on there. Indoor positioning system. That could be interesting, especially if you have like a lot of devices or you're a store trying to track people. And we will, again, get back to that. Battery, that's also pretty standard. That's how your phone knows what the battery life is like on your watch or on your headphones or whatnot. And time and clock, because a lot of times these Bluetooth devices don't actually have access to a clock in the way that you'd think, because they often don't have internet. And yeah, but with these like official services and protocols, I want to also take a look at a few kind of like proprietary ones that are kind of important at the moment. First one of these is the iOS continuity protocol. And this is, as we'll see, actually pretty interesting. And the reason for it is because if you have an Apple device, it's transmitting this right now. And it's advertising to everyone in the room that you have an Apple device and that it has specific services on it. The iOS continuity protocol does things like, for example, determining if you flip your AirPods open, it will actually send in the form of flags, like what earbud you take out of the case and all kinds of pretty crazy stuff. I saw a ShmooCon talk about this that I've linked in the references that was actually really fascinating. And he essentially used a UBERTOOTH, which we'll discuss later, to actually show iOS devices communicating in this way from the audience. He did give a fair warning for people to turn off Bluetooth, but not everyone did, which led to a really interesting demo. The other important profile right now that we should probably discuss is the COVID tracking one. You've probably heard this. A lot of places, basically every tech news publication recently has given out some kind of opinion on the COVID tracking or exposure notification system that Google and Apple have been working on. This is incredibly complicated. However, what's important is that each device is going to generate a series of unique IDs. And these IDs are going to be rotated every 15 minutes or so. These IDs are never sent to Google or sent to Apple, but they just remain on your phone. When you walk around, the idea behind the exposure notification protocol is that your phone will just record everyone else's IDs that gets sent along with the signal strength. And based on that signal strength, the device will kind of infer how far away you were, but won't actually know anything about who that person is, since the IDs are randomized and since they are actually changed every 15 minutes or so. So what this allows you to do is, if you do test positive in some way, your device will send all of those IDs that you've been using with your permission to Google or Apple, and a main collective list of all the positive IDs will be recorded on the internet. So all your device has to do is pull down that giant list and compare locally against how many the public I have COVID IDs, and it can determine if you've been in close proximity with somebody who has tested positive, and it can also give you a very rough estimate of how close you are. Moving on from that, what if I'm just like a company and I want to use an app with a Bluetooth device? What kind of permissions do I need? And the scary answer until recently for iOS is nothing. Like literally nothing. You didn't need a permission to use Bluetooth Low Energy. This has been changed, which is good. And I have an example of what it looks like if an app actually tries to use low energy. Android is slightly different. At the moment, I believe Android.permission.Bluetooth does not require a user-like interaction. However, you may run into a situation where Android.permission.accessFindLocation does. And I will get into why Google thinks it's important to classify some Bluetooth devices as requiring find location. The gist of it is, if you're looking for a very specific device and you know what device you're looking for, sometimes Google will let you get away with not having access to the location permission. But usually, as a general rule of thumb, you will need that. So why? Why would Google say you need location to use Bluetooth? Those are not the same thing. And the answer is, what if I have Bluetooth beacons or something that my phone is looking for specific? If I have like a giant big box store, like Walmart, let's just say they exist. They don't, but Walmart. If I open the Walmart app and I am trying to shop for, I don't know, eggs, and I want to know where those eggs are. So I want to open up the Walmart app to look for aisle C13 or wherever where the eggs are. What could also be happening if location wasn't required was that the device could just turn on Bluetooth and locate a bunch of Bluetooth beacons, Bluetooth low energy beacons, designed explicitly to track users. And they could use triangulation and a bunch of other technologies to figure out roughly where a user is, kind of like GPS. In addition, just an app seeing a Bluetooth beacon can sometimes give away a location. For example, if I have just one beacon as opposed to like a network of them designed for triangulation, and I enter a store, and that store has an app on my phone that's running, that's a dead giveaway which store I'm at, even if I haven't granted the location permission to that store before. Another important thing to notice here is if you were to theoretically open up that store's app and allow location to locate a store, they could have access to Bluetooth. And that would lead to a completely different problem of, all right, so my phone has a rough location and it knows I'm in the Walmart, but now with location, they can track me inside of it if they have a setup that would allow for that. And that's slightly bad. In my opinion, these should probably be two separate things, or apps that require location in that way should also require a separate Bluetooth permission like iOS does. Great, so we have Bluetooth Low Energy. What can we do with it? Well, we can build things, we can hack stuff, and we can sniff things. It turns out EDR is actually a bit harder to sniff than low energy. It's still possible, but you generally need to know encryption keys or stuff that you wouldn't get without having direct control over one end of the communication. However, LE has a few weaknesses that mostly boil down to it being designed to run on really, really, really low-end devices. Specifically, we have channel hopping and some encryption that gets in the way. For building things, though, it's actually not bad. This is an Adafruit board. Adafruit is a company designed with like a hardware hacking focus in mind, where you can buy a bunch of like types of development boards like Raspberry Pis, Arduinos, and a bunch of just generic boards. This particular one, I believe, uses the Arduino IDE. So if you've ever used that, you can program for this. And their documentation is top-notch. It's really good. I've worked with it in the past. Their documentation is easily some of the best in the business. In addition, every Pi from the Pi 3, the Pi 0, and the Pi 4 has Bluetooth Low Energy built in. So you can use that as well for a test device or to actually write code for it. Yep. All right, so let's go back to the hacking side for BLE. And let's talk a bit about what channel hopping is and why it's an issue. The gist of it is Bluetooth Low Energy, or any Bluetooth radio, is going to be essentially an SDR. It's going to be a software-defined radio, and it's going to be limited to the restrictions of a software-defined radio. Specifically, you can only listen on one set of small range of frequencies at a time, which is an issue if the Bluetooth standard has 40 different channels that you can choose from and an algorithm to randomly switch between them. Theoretically, you should not be able to follow a Bluetooth Low Energy connection during these hops. However, there's a cryptographic weakness, or not a cryptographic weakness, a weakness in the channel hopping algorithm that will occasionally allow you to do just that. It's actually really, really finicky. It often takes a couple tries to get right, but according to my reading, it's really possible to follow a low energy connection in that way and determine what hop that a Bluetooth device is going to use next. The problem is you often need sample data, and following the connection from the start is going to be really beneficial. One device that does this is the UBERTOOTH. It's kind of a Bluetooth-like development kind of thing, but I will talk about that a bit later. Like EDR, we have some encryption on the Bluetooth Low Energy side. And what I mean by occasional encryption is that while encryption is there, there's a glaring weakness. There is a particular paper that was discussed at, I believe it was the Usenix conference. I've listed it in the references at the end, but the paper did some interesting stuff and documented a cryptographic issue in not the encryption itself, but the negotiation between the BLE device and the initial negotiation between the BLE device and the central device, or like your phone or laptop or whatever you're connecting with. And essentially, if you use just works, which is basically what every BLE device uses these days, it is possible to not undo that encryption, but kind of guess your way into finding the right answer, kind of like a brute force attack. So if you catch the beginning of a BLE negotiation, you can often actually decrypt traffic. And that is really critical. So if you're trying to set up a BLE device in public and it's the first time you've used it, that might not be the greatest idea. Bluetooth's solution for this, I believe, is just to say, hey, look, use some actual authentication, use some crypto on the application level side. And for the most part, that's exactly what you see happening. For example, my smartwatch, which uses BLE, is entirely encrypted on the application side of things. So even though the BLE layer does have some encryption, the smartwatch doesn't trust it, and it just uses its own. So with that said, what can you do? BLE Wireshark captures are kind of hard to get. It's hard to get a PCAP with Bluetooth in it because of the restrictions I've mentioned before. Well, you can use Android debug logging. There is a setting on Android devices that you can enable in the developer section of the settings page that will allow you to record all Bluetooth packets sent or received directly to a PCAP file that sits on the main storage. And you can just pull that off and do as you wish. This is a really good option if you're trying to figure out how maybe an app on your phone is communicating with a Bluetooth device, since you won't have to have any equipment other than that phone, and it's super easy to set up. The next option is an UBERTOOth, which is kind of like, as I mentioned before, a packing SDR toolkit for Bluetooth. With Wi-Fi, you can kind of use most wireless cards in laptops to actually listen and capture packets through like Wireshark or otherwise. Bluetooth doesn't really let you do that. Most things in Bluetooth are kind of closer to an API with your device kind of communicating with the Bluetooth chip itself and sending commands that way. And most Bluetooth chips will just not expose anything relating to capturing packets, especially since the 40 channel thing and channel hopping is quite annoying to deal with. They just won't do it. Lastly, you can actually use Bluetooth like exploring apps. The one I've had good luck with on Android is NRF Connect. If you download that, you can kind of scan for Bluetooth devices in the area or Bluetooth low energy devices in the area and see individual characteristics and services on those devices that are being advertised. You can also use Bluetooth CTL on Linux, although that's incredibly buggy, as I discovered last night. BetterCap has support for Bluetooth as well. And the STLE project is the tooling that allows for that cryptographic weakness to be exploited. It has the code for taking a Bluetooth pairing session in and actually spitting out a encryption key that you can use. I've mentioned this a bit. This is an UBERTOOth. It's essentially an SDR. It sits on the 2.4 gigahertz band, and it can use those BLE channel prediction algorithms to kind of figure out where a BLE device is going to try to communicate next. And this is what you'd use if you have two kind of black boxes of, I have a BLE device talking to a BLE device. I have no access to either, and I actually want to figure out what's going on. STLE tool, again, I mentioned this earlier. That is the paper in question, if anyone is interested in reading it. It's super simple. You give it a PCAP from an UBERTOOth, and you output a decrypted PCAP. It makes it pretty easy, and the only thing it needs is the entire pairing exchange between the two devices, which, depending on your use case, could be kind of hard to get. All right, at this point, I'd move on to the demo, but since we're going slightly offline for the demo, does anyone have any questions? I know I covered a lot of material very, very quickly, and I have a feeling there might be a few.
Someone asked you to upload slides to the workplace, but that's about it.
I'll do that immediately after.
What got you into Bluetooth?
I was working on a project for work that used it. And I learned way too much about the Bluetooth standard really quickly. The question that was asked for the stream was, what got me into Bluetooth?
Yeah, for the channel hopping, you talk a lot about the channel hopping. Is that like a hardware side? Is that like implemented on the hardware side, or is that a software thing?
Kind of both. So it is a software thing, but it's a software thing implemented on the BLE chip.
Okay.
So essentially, it's going to be abstracted from you from an application perspective, you're not going to see any of that. It's just going to happen in the background on the chip. Oh, the question was, I mentioned a lot of channel hopping. Is that a software thing or a hardware thing? Do we have any questions, John?
I do not see any.
All right.
Awesome. You just hit stop recording on the Stream Boy.
All right, I'm going to drop my screen share real quick.